let's begin with some announcements here. So I've just posted. Now, you turned in your projects, right? Great. I'm looking forward to reading them, and I think that probably it will take me less time to go through them because I've already seen you work at several previous stages. So, I mean, between now and the final, which is Friday of next week, I'll have them graded, and hopefully much sooner than the final. So good job on the project. I hope it was a useful learning experience. I've got a lot of positive feedback over the years from students who felt like this was maybe the first time they'd seen iterative design, where you have to make an adjustment, look for improvement, make an adjustment, and so on. And I think the other benefit of a project like that is that now you've got some real experience with software that you can put on your resume. I mean, and it's not kind of like false boasting or anything. You've got the same level of expertise using that software as a lot of relatively junior engineers who've only used it a handful of times. And so if you haven't already, I'd encourage you to update your CV and include water gems to the list. All right, so with that said, you've got a homework assignment due on Friday, and that has two problems on it. One of the problems is related to the direct step method, and the other is related to sewer design, which is what we're talking about today. So I don't think it's an especially heavy lift for that assignment. I know that you're busy with lots of things this week, and so I wanted to try and keep it light. That's due by 1 o'clock on Friday. Now on Friday we're going to have another one of these online class meetings, and I know there's been kind of a lot of them. This past week on Friday it was because of the Virginia's conference, but a lot of the other Friday meetings that we've had to have online is because I'm the vice chair of the graduate council here at Marshall, and we have our monthly meetings on Friday at 1 p.m. So it's not like I'm just getting out of here and having fun. I'm sitting in a meeting that's far less interesting than anything we could be doing in here. So felt like maybe I should explain the fact that we've had a lot of Friday online meetings, including this one. I'll be at the graduate council. So for the Friday lecture, it's going to be related to HECRAS, which is some free software that's made by the Army Corps of Engineers, and it's used for water surface profile calculations. And I'll have a demo that you can work through in that video, and if you send me evidence that you've worked through the demo, and I'll explain that to you in the video itself, before Wednesday the 28th, then I'll add up to 20 bonus points to your homework grade. And I mean, that's quite a lot. We've had some assignments that were only worth 40 points, and so it's like, a pretty good dose of extra credit. The final exam, which we're having next Friday, is comprehensive, covering all different topics from the semester. And you should bring your laptop computer to that exam because there will be some problems where you need to use Excel, most notably the water surface profile stuff that we've been doing in recent days. But also I'm going to include a water gems problem to try and give you a little bit of recognition and credit for the experience that you've gained using that software. You can bring 3 equation sheets, and so you could just reuse the equation sheets that you developed for the first 2 exams, plus add 1 more into the mix. And then I'm also going to provide that same equation packet that's been posted online all semester long. So does anybody have announcement-related questions before we start talking about sewer design? All right. So sewer design is in chapter 16 of your textbook. If you're in the habit of following along, that's great. I think it's good just to see how the author puts it and some of the complementary explanations that can go along with what we talk about. Sanitary sewers, that has to be maybe one of the most ironically named things in civil engineering because they're anything but sanitary, but we're a lot better off in having these separate systems that carry wastewater without us having to mingle. There are a lot of places in the world where sewage just runs in open ditches through the streets, or a lot of places where they have combined sewers, which is unfortunate because in the case of combined sewers, the wastewater often ends up in creeks and rivers. And so there are some places here in Huntington where we have combined sewers, but over the years they're trying to switch those combined sewers into separate sanitary sewer and storm sewer. It is open channel flow. You know, down here at the bottom of the sewer we've got a circular pipe, and it's not pressurized flow. So we wouldn't use Darcy-Weisbach equation or the Hazen-Williams equation for calculating head loss through a pipe. Even though it is pipe, it's open channel flow. So we use Manning's equation to describe the hydraulics and the friction that occurs in sanitary sewers. There's just some broad terminology that it's useful to know when people talk about service connections. What their meaning is where the wastewater comes out of an individual residence or a business. A manhole is simply a location where there's access to the surface at spaced intervals, maybe anywhere between 300 to up to 800 feet, where you could send in a little inspection robot that has a camera on it, or sometimes they'll have vacuum trucks that can try and vacuum up any sludge or sediment that settles to the bottom. Excuse me, because these aren't just carrying liquid water, it's carrying anything that gets flushed down the toilet, including human waste, food debris gets into sanitary sewers, a lot of things get flushed in there that isn't necessarily that, you know, like wedding rings, and sometimes in the case of combined sewers, then there's an inlet at the street that's bringing in storm water, and then you could get everything from car parts to kids' balls, and all sorts of stuff can go through the sewer. Excuse me. Most of the time the water is flowing according to open channel flow, but occasionally there will be pump stations in a really flat area that doesn't have much slope. Then they'll have to have the sewage flowing downhill and then lifted back up towards the surface, because if you have a relatively flat area, then the pipe has to be angled downward in order for the wastewater to flow, but then there would be some sort of a vault where the water accumulates and then is pumped again to another open channel flow that's closer to the surface. And so it'll be flowing by gravity and then pumped up, flow by gravity, pumped up, until it finally comes to the location where the wastewater is being collected and treated. It's hard to overestimate how long sewers may be put into service. There are plenty of sewers in the area here that are well over 50 years old, and a lot of communities in the United States where the sewers are more than 100 years old. And so if this infrastructure is going to be in place for that long, you have to be very careful in thinking about what the future conditions will be and sizing the pipe for the flows that you expect in the future. So if you're in an area that's already pretty well established and built up, then maybe your current day flows are a good estimate for what you'll have in the future. But if you're developing a new area that only has a few buildings, and there are a lot more homes or businesses that are going to be put in, and if there's going to be a lot more impervious area added to the watersheds that could increase the amount of runoff that gets into the sewer, then you have to really be cautious to make sure that there's enough pipe size to accept all the incoming flow. And the other thing about the flow that gets into these sewers is that it varies throughout the course of the day. In the same way that water demand flows through cycles of high demand in the evening and low demand overnight, water into the sewer also follows that same kind of pattern. And so there's a big variation in the daily flows. Besides the water that gets into the sewer that we actually want to be there, like the water that goes from your sink or that gets flushed down the toilet, there's also a lot of unintended or unwanted water that gets into sewers. And those are often called I and I, those waters that get in unintentionally or in an unwanted way. The first I of infiltration is related to cracks in the pipe or poorly connected pipe where there's groundwater that seeps in to the sewer. And those sorts of flows are relatively constant over time because the groundwater levels don't rise and fall too quickly over the course of a day. Inflow, on the other hand, is usually related to extra water that gets into the network through storm events. And so if there are roof drains connected to a sewer, or manhole openings, or in some cases illegal connections that are unmetered or unregulated, then the extra water that comes in and varies due to wet weather events is the inflow. So here in the picture you can see a crack in the pipe and water kind of streaming in around the seam. And then this is a picture of a roof drain where instead of discharging the stormwater onto the surface of the parking lot, it's going down and connecting into the sewer. And so that's adding flow to the pipe, and it would be related to the entire area of that business's roof. So when you are trying to estimate how much water is going to come into the sewer, there's on the one hand the reality of the situation, which as an engineering estimate would be related to the number of people that are there, related to the quality of the pipe that's put into place, the age of the system. But in a lot of places there's also municipal regulations that tell you what to assume, so that you actually don't have the flexibility to size the pipe based on how much water you think there will be. You just size the pipe based on what the guidelines tell you to assume. So for example, there are some places like Milwaukee where their city ordinance says that you should assume 1,000 liters per person per day when sizing a sewer. Plus they say to allow additional capacity in the pipe for inflow and infiltration. So that's a really high per capita water assumption. But then there are other cities like in Berkeley, California, their regulation says to assume 350 liters per person per day when you're sizing the capacity. So basically you just have to know who are the government entities that regulate and what their requirements are in order to calculate the correct assumption for how much capacity to allow in the pipe. A lot of these are dependent on the population density. And so you're putting in pipes that aren't going to move around because they're buried underground. And so if an area is going to have single family homes with each lot is an acre in size, then you're going to be generating a lot less wastewater in comparison to high density housing where it's maybe multi-story apartments. And so having a clear idea of what's the area going to be zoned for is an important part of being able to size the sewer pipes appropriately. Here are just some typical guidelines for different types of densities that are assumed for when sizing sewer pipes. As much as 2,500 people per hectare in the case of multi-story apartments. Commercial assumptions and industrial contributions to wastewater is largely the similar approach of just knowing either how many people are going to be in an area, or in some places, rather than calculating the number of people and what they're doing, they just give you an assumption for how many liters per day to apply for a certain area. So here, for example, it shows that in Memphis, Tennessee, they suggest that in commercial areas you should provide enough sewage carrying capacity for 19,000 liters per day per hectare in commercial areas, where Santa Monica goes as high as 91,000 liters per day per hectare. A lot of industrial facilities will have their own wastewater treatment facility, and that may be like food processing plants or slaughterhouses or metals processing plants will have some kind of sewage treatment system, in part because the discharge that they generate is too concentrated or toxic to go into the municipal sewage treatment. And so in those cases, if you're aware of a facility that has its own wastewater treatment, then that would maybe modify or eliminate completely the requirements for sizing the sewage pipe up to their facility. Infiltration and inflow and peaking factors are partly related to the population that's being serviced in a particular area. And the older a network is and the more cracked the pipe is, they generally assume that there's going to be a lot more infiltration and inflow. But if the construction has been well inspected and supervised and they have a good bedding down and the pipe is unlikely to crack, then they may be able to decrease the assumed contribution of infiltration and inflow and have smaller pipes as a result. So as far as the peaking factors go, it's related to the population in thousands. And this is kind of similar to an idea that we've talked about before, that in a small town, it may be that people have a more similar schedule, where if you have a small town and it's not very spread out in terms of geography, and people follow about the same hours, then there would be a much larger peaking factor that has to be applied, because the water isn't experiencing what's known as routing. And routing is just talking about the delay that occurs when in one part of the network, let me just show you just a quick sketch here, that if we had a dendritic pipe network, meaning that all of the water is coming to like a sewage treatment plant, but it's coming from lots of different directions. So we've got pipes that are feeding in from some town, and they're all flowing downstream towards this treatment plant. So if everyone in a large spread out city flushes their toilet all at once, it's going to take some time for the water that is here to make it to the treatment plant. And the water that's closer is going to get to the treatment plant more quickly. So in a big network, even if everyone takes a break in the middle of the Super Bowl and flushes the toilet all at once, the peaking effect is less severe than the peaking effect in a smaller town where the travel times aren't as long. And so there's kind of two simultaneous things that makes it more extreme in terms of the effect of a small town versus a large town. A small town has larger peaking factors because it's more likely that people will have similar schedules, and then it's also that the travel times are lower. Whereas a big city like, let's say, New York City, they call it the city that never sleeps, and so some people are working the night shift, they're doing their dishes at 2 a.m., some people are working a day shift, they're doing their dishes at 8 p.m., and because of the irregularity in schedules, both commercially, industrially, and residential, the peaking factors compared to the average daily flows are less extreme. So these empirical equations kind of tell you what would be the minimum flow rate that you'd see compared to the average daily flow rate as a function of population in thousands, and then the maximum flow rate that you'd see compared to the average also in terms of the population in thousands. All right, so let's talk about the hydraulics of sewage pipes. And most of the time, the pipes are not flowing full, with occasional exceptions to that. Let me show you this kind of funny video, which is on a rainy day, a combined sewer that had an unexpected hydraulic event. So we're looking at a roadway, obviously. Yeah, that's a lot of water. People just driving right through it. So there's a place in Barbersville, not quite as dramatic as this, but it's on Route 60, and if you drive by in wet weather, you can definitely smell that it's a combined sewer. Oh, a car ran into this manhole cover. That's kind of too bad. Oh, it's going to go again. Fast forward a little bit. He's walking around. Oops. Okay. So, just the spray never ends. He's running. He's running. Other people's misery. All right. I forgot that he was running. All right, so most of the time the sewer isn't full. And the geometry of that is relatively complicated, just in terms of finding out the relationship between the depth of flow and the cross-sectional area the wetted perimeter. Those things are pretty easy for us to calculate, area, perimeter, depth, if it's a rectangular. And you're pretty good by now at calculating the trapezoidal geometry. The partially full circular pipe, though, is on a next level in terms of complication. And what I'll start off in mentioning is that what we do is we measure the angle from the center of the pipe down to the water line. So you can see these little dashed lines here. And then theta describes the angle measured in radians. So for example, if the pipe was half full, then that would be pi radians, right? So if it's 180 degrees, then that's pi radians. So when you know the angle in radians, then you can calculate the depth. Here it's labeled as h, compared to the diameter of the pipe. If you know the angle, then you can calculate the cross-sectional area as a function of the angle in radians and the diameter of the pipe. And wetted perimeter you can also calculate. If we put all of those into Manning's equation, so here's Manning's equation, and if you substitute in this for A in those locations, and if you substitute this for P, then what we end up with is an equation where we can find the relationship between flow rate, diameter, slope of the pipe, and then the angle. Pretty complicated expression of Manning's equation, but we can make it work. Now, one of the things that adds additional complexity to this is, remember that n value in Manning's equation talks about a roughness. It's a pipe roughness. And until now, we've always just had a single n value that applies for a certain type of material. But when we have a partly full pipe, we have to correct and find an adjusted n value because there's less wetted perimeter if you have, well, there's relatively less wetted perimeter on a cross-sectional basis for a full pipe compared to a relatively shallow depth of flow. So like as it's shown right here, the depth that's shown in this picture, there's a pretty long wetted perimeter compared to a relatively small cross-sectional area. And so the effect is that the n value should be higher than it ordinarily would be if we were calculating the flow rate for a full pipe. So I'm going to show you an example where we will solve for partly full flow in a couple of different ways. And one is using this nomograph, where you could calculate what's the flow rate of the pipe if it was full. So that's Q full. So if you find the flow rate of the pipe if it was completely full, and then you know the depth of flow compared to the diameter, then you could use this figure to say, well, if I know the full flow rate and I know the ratio of the depth to the diameter, then you could go over here, find the point of intersection, and then down with the horizontal axis would be the flow rate compared to the full flow rate. So that's one method with the nomograph. And we're going to use this example to illustrate for a 24-inch diameter concrete pipe, where if the water was flowing full, the n value we should use there is 0.013. The flow depth is 9 inches, and we've got a 0.5% slope. We're going to use the nomograph method, first of all, by calculating what would be the flow rate if the pipe was full, and then finding out the flow rate when it's partly full, based on the nomograph. And then the second way we're going to do this is using all of these kind of crazy angle methods. We'll solve for theta, then we'll solve for the area as a function of theta, solve for the wetted perimeter as a function of theta, and then substitute all of those into Manning's equation. All right, so let me clear off the whiteboard here and just kind of set the stage for this first part. If we had a full pipe, then Q full is going to necessitate us calculating the cross-sectional area, for example. So if you have a full pipe, then the cross-sectional area is pi d squared divided by 4. And so in this example, 24-inch pipe is 2 feet of diameter. So that's pi 2 feet squared divided by 4. So the area, if the pipe is full, is 3.14159 square feet. And the wetted perimeter, if it's full, is pi d. So that is just pi times 2 feet. So it's 6.283 feet. Okay, so the full flow rate, Q full, is going to be just me substituting into Manning's equation here. Now, 1.49 is the prefix that we only use for traditional units. If this was in SI units, then we wouldn't use 1.49 in Manning's equation. But this is traditional, so I'll add 1.49 times the area, 3.14159 feet squared to the power of 5/3. Our slope of 0.005 to the 1/2 power, and then n value 0.013 times the wetted perimeter, 6.283 feet to the 2/3 power. All right, so if we do the calculations there, we should get that the full flow rate is 16.04 cubic feet per second. So that's what it would be if it was full, but it's not. It's flowing at 9 inches. And so what is Y to D? It is 9 inches out of 24 inches. Okay, so that ratio is 0.375. Okay, so we go to this figure and we find 0.375. So here's 0.3 on the vertical axis. Here's 3.5. Here's 3.75. Okay, now I'm going to go over and I'm going to intersect this curve. Okay, so going over. Now it's just a coincidence that it's intersecting those two lines together. Don't read into that at all. The curve that we're interested in is this one. So 0.375, intersect the curve, and now we're coming down to the horizontal axis, and that ratio is Q to Q full. I read that as 0.24. Okay, so here's 0.2. This would be 0.3. So it's like 4/10 of the way between the 0.2 and the 0.3. So I called that 0.24. So 0.24 is Q to Q full. All right, and let me just bring up the solution so that this is included in the video. Okay, so if 0.24 is the ratio of Q to Q full, then Q is Q full times 0.24. So when it's flowing at a depth of 9 inches, then it's only going to be 3.85 cubic feet per second. It's a nonlinear relationship. That's why this curve isn't just a straight line. Where was that curve? This one. Nonlinear. If it was just a linear relationship, then it would just be at a constant angle. But it's a nonlinear relationship because there is, you'll have a certain increase in cross-sectional area, but the wetted perimeter is increasing at a slower rate, and then the wetted perimeter increases at a greater rate. So any questions on this first part using the Nomograph method to find the flow rate for a partly full pipe? Okay, so for the angle method, I am going to pause and allow you to try and calculate theta. So if it's 9 inches out of 24, so y is 9, d is 24, then what is the angle in radians? So if your calculator's not in radians mode, you'll need to put it into radians mode. Now this cosine minus 1, on my calculator, that is the ACOS function, inverse cosine. So we want to know what is the angle when we've got, in radians, 9 inches out of 24. Okay, did anybody else get 2.636 radians? Okay, good. So we know how many radians there is. Now we can substitute that into our equation for area, which we need, and wetted perimeter, which we need, because we're going to substitute those into Manning's equation. We need to know the area and the wetted perimeter here. So for example, the area is going to be theta minus sine of theta times d squared divided by 8. Isn't that strange that you've got the angle minus the sine of the angle, and that those two are going into the same function? I find it very strange. So it's going to be okay. Who got the area? Anybody tell me what the area is?
I got 1.075.
Good. 1.076 square feet. That is right. And wetted perimeter. That one's, I guess, a little bit easier. 2.636 feet. So okay, so we found the angle, and from that calculate the area. And the area it's talking about is not the area of the pipe. You know, the area of the pipe would be pi d squared divided by 4. It's talking about the area of the part that's carrying flow. So the area from the water line down to the pipe material. That's the area it's talking about. And same thing with the wetted perimeter. The wetted perimeter is not the entirety, the wetted perimeter of the whole pipe. It's just the wetted perimeter that the water is actually in contact with the pipe material at that depth. Okay, so we've got the area and the wetted perimeter. Now this part about correcting the end value, we again have to turn to the nomograph, because it's this top horizontal axis that we use to find the end value when it's partly full compared to the end value when it's completely full. So our y to d is 0.375. So that is, here is 0.3, 0.5, 0.375. So now we go over, oh, I'm so tempted to write on that. We go over and then up. So this is our Manning's end curve. So we go over and up and find that intersects here. I call that 1.27. So the ratio of end to end full is 1.27. So that means the end value when it's full is 0.013 for concrete. That was given in the problem statement, that the full end value is 0.013. So now the end value when it's only partly full is even higher. And the reason why it's higher is because there's more wetted perimeter relative to the amount of area that's present. So we have to correct for that effect. So we've got now, in Manning's equation, we've got the area that we calculated for of 1.076 feet squared to the 5/3 power. We've got the slope of the channel, the corrected end value, the wetted perimeter, and then if you calculate all that, you get 3.78 cubic feet per second. Now that's not exactly the same as when we calculated it the other way by the nomograph, but I mean, keep in mind that we're using this nomograph and I'm just kind of dragging my finger across the paper. So, I mean, it makes sense that there's going to be some variation, and on a percent basis, actually, these two answers are very close. 3.85 versus 3.78 is less than 2% difference, according to these two different approaches. And so, that's sufficiently accurate, considering that Manning's equation is based on a pretty rough approximation of the n value anyway. So this is how we handle the hydraulics when a pipe is only partly full. And with that, you can get a start on the homework assignment that's due on Friday. There might be a couple of additional things related to BOD, which I'll talk about in class on Wednesday. But that's all we've got for today, so I'll see you then on Wednesday.